Hey, we're Team Amanda, and in this presentation we're going to go through the basics of software engineering.
In the 21st century, software has come a long way. Nowadays, it's used in almost every industry from medicine to agriculture, transportation, and so on. It's become an important aspect of our daily lives. So how has software changed? Before the 1970s, there was only mainframes with single processors, and only two types of computations could be performed. Transformations, which is turning an input x into an output y, or a transaction, where an input determines the function being performed, like a bank deposit. It was really simple back then. However, in the 21st century, computers now run on multiple systems with multiple functions. There are also many more applications, such as mobile devices, streaming, big data, Bluetooth, AI, and more. In the 21st century, we're also faced with many challenges. First, we need to be able to maintain or update legacy systems, some of which where the original engineers might be retired or long gone. Second, we need to be able to deal with the lack of experience among the people in our profession, with about half of software engineers having less than 5 years of experience. Third, and most importantly, we need to deal with increasing speed of advancement and increased pressure to deliver software faster. We can't let business needs overwrite ethics, good design, and secure procedures. Software evolves continuously. After the initial requirements, we assess the existing system and propose system changes and modifications to create the new system. 90% of the cost of software is maintenance. The goal of this system is to fix bugs and make incremental enhancements. Software evolution focuses on adaptation and migration. Given a problem, you need to analyze the problem and synthesize a solution. Analysis involves abstracting a problem into multiple subproblems. Synthesis involves combining the subproblem solutions into one large solution. There are many tools we can use to aid us in problem solving. There are source control tools such as Git and team management tools such as HP Agile Manager, for example. There's no reason to reinvent the wheel, so use a lot of tools. Software engineering combines the theories and computer functions from the study of computer science and the realistic customers' problems in order to create tools and techniques to solve those problems.
So let's try to define what is a software engineer. A part of being knowledgeable, a software engineer needs to know how to communicate with his workmates. He needs to understand best practices of developing software and also being honest whenever he makes a mistake. Another important part of being a software engineer is to keep on trying. When you keep on trying and come up with different solutions to the same problem, you might figure out the best solution to that problem. And remember that communication is a key, and you can talk to many people in your team and other teams about the project you're working on. You can talk to the client services representative, the solution architect, the QA guy, and the project manager, and understand exactly what the client wants, how the client wants it delivered, and how did the client react to the previous feature.
Human errors can lead to faults, which can then lead to failure. A fault occurs when a human makes a mistake, called an error, performing some sort of software activity. A failure is a departure from the system's required behavior. An example of this would be when the IRS hired a company to build a tax form system that didn't work as intended. They lost over $60 million due to the faulty system. In more extreme cases, safety-critical systems can cause threat to life or health when failures occur. An example is the Therac 25 machine that killed several people. In short, it's important that we create software that's safe and reliable.
So what does define good quality software? Well, it depends who you ask. The CEO would want the software to be popular and last forever. And the CTO might need the software to be fast and develop really quickly. The CIO might want the software to be integratable to other projects to save money. But a client would want completely different things. It would want it to be easy to use or easy to be adjusted and so on. So it really depends on what the software is aimed for.
There are two main views of what makes good quality software, the user view and the developer view. The user wants it to perform the intended task, easy to learn, easy to use, etc. And they're more concerned with external aspects of characteristics, whereas the developer wants it to be fault tolerant, have good code design, efficient execution, and they're more concerned with the internal characteristics. And there are many quality models, such as McCall's, which we're going to see on the next slide. So here's McCall's quality model. For example, simplicity, conciseness, self-descriptiveness, and modularity are all a subset of maintainability. If you meet the quality requirements of all the subcategories, then you can meet the overall quality of the software. Just as the product itself needs to be high quality, the actual development process and maintenance process should also be high quality. We can follow one of the existing quality models, such as McCall's, or we could create our own. Why does the company need this software? If it is not really needed, then there's no need to implement it. The business value must increase for it to even be considered. The business industry defines ROI one way, and the software industry defines it quite differently. In '95, these guys surveyed these companies and asked them to list some ROI items, and there they are. People view the quality of software differently. There's a transcendental view, user view, manufacturing view, product view, and a value-based view. So the transcendental view is where quality is recognized but not defined. They could say, the software is really good, I don't know why, it's just as good. And then the user view, quality is fitness for purpose. It does what it says it does. The manufacturing view is quality conformance to specification, typically how the developer views it. They followed the requirements, therefore it's high quality. The product view, quality is tied to inherent product characteristics. The product does something that other software doesn't do, so therefore it's a great product. And the value-based view, where quality depends on the amount the customer is willing to pay. The software does a good job for the price. There are three main participants in the software process: the customer, the user, and the developer. The customer is the individual or company responsible for paying for the development of the software, and communication with the customer is key to create a quality product. You should document everything before the coding even starts. Then the user is the individual that actually uses the software on a regular basis. They view quality from the outside of the system, typically. And the developer is the individual or company responsible for building the software system to the specifications. They need to know the needs and wants of the customer as well as the user, and sometimes the lines separating these participants can be blurred. Participants can end up wearing multiple hats. So who does the software engineering? There's different factors that determine how many people will end up working on the software system. The size of the project, difficulty, financial constraints, time constraints. So anyways, it's a group effort. It takes input from the user, customer, and developer alike. So we need to know the boundaries of the project. Where does it start and where does it end? It may be beneficial to approach the product as a system. In a system, there's an activity, which is something that happens in the system. Objects are the elements involved in those activities, and then we need to know the relationship between them that has to be clearly defined. Examples could be human respiratory system, automotive cooling system, computer system, etc. Here's an example of a system, the respiratory system. So the objects are the mouth, nose, lungs, oxygen, carbon dioxide, and the activities are inhale and exhale gases and filter them. So for instance, we need to know the relationship between the objects and the activities, like the mouth inhales gases, the lungs filter the gases, and you could also exhale the gases from the mouth as well.
So just like the human body, the software can be also separated into subsystems. My best advice would be to separate the subsystems into verbs. For example, what the software does, if it's pressing a key, or displaying information, or calculating. Each verb should have its own subsystem. The connection between each subsystem should be very strict and minimal. Let's take a computer game as an example. Let's assume you are a spaceship and you move between obstacles and need to shoot them down. So the keyboard or the key press, the verb press, is going to be a subsystem. It will take the input and convert it into data. The score system, which will calculate, that's the verb, will calculate the points you gather through each level. And last system would be the high score system, which will persist, that's the verb, persist the information into the file system, so you can compare it later against your friends. So should a software be easily changeable? Once again, the answer for this question is it depends. The software should be easily changeable because the client would be happy, it would fit its requirements, the job would be easier, and the company will be able to reuse the software anywhere else in the company. However, it's important to remember that the architecture of the software is what makes it easy to change. And if you change the architecture itself, then things start to break down and gets messy. So you need to remember that whenever you change the software architecture, you need to look how it was done in the past and slowly and moderately change the software. The key answer is balance. So the architecture should guide the engineer to where to make the changes. And any changes need to be considered slowly and carefully.
Prototyping can be defined as building a small version of something you are trying to create in the end. It's important for software engineers and designers to develop good user interface so that users can use their products very simply. Shown here is a prototype for a UI created for a car site. Software architecture is how the system is created in terms of architectural units and the relationships between them. Some decomposition techniques include modular, data-oriented, event-driven, outside-in design, and object-oriented. There are many variations of the software process, including enterprise-wide, division-wide, departmental, or single-user productivity. These variations help with control, speed of development, and project management. Characteristics of small to large-scale software development. It's a top-down approach with enterprise at the top and single user at the bottom. Controlled development works downwards, while the rapid application development works upwards. Less people working on a project means more control. However, more people working on a project means quicker development. The figure shown here shows the small to large-scale software development in a hierarchy with enterprise at the top and single user at the bottom. Software reuse is defined exactly as it seems. It is reusing old parts of code, software, or a whole project in itself in a new one. This helps reduce costs as well as increase productivity since part of the work is done for you already. The figure shown here shows how quantifying design is done. Tools and integrated environments can help software engineers. These include platform integration, presentation integration such as UI, process integration such as links tools in dev process, data integration such as sharing common data, and control integration where one tool can call and control another one. In the question of is there a software crisis, for example the Ariane 5 rocket on June 4th, 1996, the rocket malfunctioned and veered off course 40 seconds into the launch, costing approximately $500 million as it contained 4 satellites on board. This failure was a result of a design error, so this does lead to a problem in software engineering. This figure shown here is the Piccadilly system. It was a system designed for the Piccadilly television program, which controlled the advertising for a given show at the time.